Hello, everybody. Welcome to our November Gazebo community meeting. Let me start by sharing the screen with the plan for today, because we have a full agenda. We'll start as usual with Addisu talking about the next a few Gazebo announcements, some Gazebo news, etc. And then the topic for today is going to be the NASA Space ROS Simulation Summer Sprint Challenge. It's a long name. And we have many guests today. So some of the Gazebo collaborations or Gazebo contributions to this challenge are going to be presented today. As you can imagine, we have many talks and we're going to try to be fast. So we will we will recover the spirit of the lightning talks at ROSCON, I feel. We have 5 minutes max for each talk. So please stick to the time. For the sake of time, I'll check to make sure that we don't go beyond those 5 minutes. I don't think we'll do questions until the end, and only if we have time, just to make sure that everybody has the opportunity to go there. We have also Andre, who was also nice to talk about another contribution to this project. I feel that Andre's talk is a little bit shorter, but I think hopefully we'll have room for everybody. And then if we have time, we'll do questions. So this is going to be the order of the talks. It's in the agenda. Just if everybody can take a look and be prepared for minimizing the transitions. I'll mention who's next, etc. And that's the plan for today. So let's start with the announcements. Addisu, are you ready? Thank you.
All right. Thanks, Carlos, and welcome, everyone. Thanks for attending this Gazebo community meeting. For this month, we have a bunch of end-of-life announcements. So I don't know if you've seen this, but we've posted some of these on the community discourse. The first one is Gazebo Garden. That one has actually reached end of life. It was a standard sort of lifetime. It wasn't a long-term support version. And we're just doing the last few touches and making the last few releases before we actually archive all the repositories associated with that. And so, if you're on Gazebo Garden, you highly recommend it to migrate to Gazebo Harmonic. Gazebo Citadel is the next one, and that one is also coming to end of life in December. That was our first long-term supported version. It was supported for 5 years. It's hard to believe that it's been 5 years, but yeah, so that's also coming to an end, and that's the only one that I believe supported ROS 1, ROS Noetic. So please migrate to ROS 2 and Gazebo Harmonic or Ionic. And then the last one is Gazebo Classic or Gazebo 11, and that one will also reach end of life in January. If you don't know what this is, please, I'll post the link on there to help you migrate to the new Gazebo. But this one is coming to end of life as well in January. And we've added banners. If you update, you'll see when you start Gazebo Classic, you'll get a notice that it's reaching end of life. The next item is that the reinforcement learning interface work has started. We've announced on at ROSCON, this is one of our items in our roadmap. Arjo has been working on this and has made some progress. This is just a quick video to show some progress here and showing how we can already use some algorithms to do RL to balance a cart pole. There's a lot of things that need to be done in Gazebo to make this more streamlined. So there's ongoing work, and we welcome more input from everyone. This is if you've been using reinforcement learning with Gazebo, or if you want to, and you have some ideas or pain points, please go and chime in on that issue. And I think that's all I have. So thank you.
Thank you, Addisu, for all the news. And yeah, hard to believe about all this end of lives, and all the time that's elapsed. All right. So next topic in the agenda is these contributions or these talks from the NASA Space ROS Simulation Summer Spring Challenge. So what is this about? I think NASA doesn't need introductions, but what is Space ROS? So I have a link here. This is the GitHub page of Space ROS. So you can take a look at all the different repos and all this project, all the resources available in this project. But essentially, it's just one of these open source projects that's based on ROS2. And essentially, this is to handle the particularities of space robotics applications and in particular the safety aspects associated to this. So there's documentation, there are repos here, there's a simulation part, and this challenge was announced by NASA over the summer, I guess, on the North Hemisphere. And the idea behind this project, or this challenge, was to look for improvements in the Space ROS repositories, in particular, like increase the fidelity of the demonstrations that were there, the simulation worlds, or adding extra capabilities, extra features to these projects. So this is the context of all the talks that we're going to see, and all of them are going to be summaries of the contributions that these people and contributors made to that project, to the Space ROS organization and project. So we're going to start with Sanjay JP from Purdue University, and then next in deck is David. See if you can also be prepared. Sanjay?
Hi, Carlos. So can I start?
Yes, take it away.
Thank you. Once again. Is my screen visible?
Yes.
Okay, thank you. So yeah, first of all, thank you, Carlos, for this invitation to this Gazebo community meeting to showcase our work. Yeah, so a quick intro about me is I'm a first year master student here at Purdue University in United States. So the main reason I want to work on this challenge was that I wanted to contribute to something meaningful in the open source community, and as well as I wanted to apply my theoretical knowledge, whatever the subjects I have taken, in a practical application, and this was such a wonderful opportunity for that. So yeah, the title is Cooperative Autonomous Distributed Robotic Exploration. So the NASA is planning to send this 3 rovers of this to moon to explore autonomously and collect the data and show a potential in multi-robot missions in 2025. So that was the idea of this one. And here is a small video of from NASA's website of what they're planning to do. Yeah, so the overall project summary is that first, the objective was to develop a ROS-based simulation for this NASA planned Cardio Trio mission to map the moon scheduled for spring 2025. So first, in order to do that, I need to design a lunar landscape. So I used the public image from NASA's gallery to design that in Blender. Next, I collected all the world parameters for the gazebo, such as gravity, atmosphere, pressure, and all those from the fact sheet from NASA's website. Next, I developed this CAD model based on only the images and the information given. There's no specific dimension images. I just use the images to redesign this from scratch, and used SolidWorks UIDF extension to convert it to UIDF format, and used ROS to humble. Next, for simulation integration, I used sensors such as normal differential drive controllers, IMU, LRF, RGBD sensors. Next, I developed a small Python code to utilize this RGBD or LRF to get the point load data and map with always with respect to the lunar, which will be the fixed frame. Next, I developed a small Python GUI for teleoperation control of this individual rovers with a small display for that RGB image. Next, I tested this on WSL, Windows Subsystem for Linux. Nowadays, people don't need to dual boot it necessarily. They can still use the Windows Subsystem for Linux. And as well as if they have any VMware or some workstation, they can use this also. So I have tested on both. It's working both. And I have made it open source, SolidWorks CAD file as well as Blender files. If people want to make more changes, they can do it. And future workers, I'm planning to implement a multi-agent reinforcement learning algorithm to coordinated mapping of the moon. So next plan is that. So first, here is a quick video of how I started. So I took the image, then in the Blender, I added the image. I used the tools to create the surface of the lunar for the gazebo. And this was the lander which I designed in the Blender. Next is the CAD design of the try robot. So I just use single UIDF. I use namespace in all the UIDF so that whenever in the launch file, if I give it new name, robot 1, robot 2, robot 3, or CAD 1, CAD 2, CAD 3, I can spawn how much ever robots I want. So that was one more new thing which I learned in this. And this is the integration of all UIDF in the gazebo as well as ROS. So this is the whole environment, and these are the try robots, and this is the lunar lander. And here's the GUI which I created. So I'm able to control individually based on robot 1. I have right now I spawned only 3 robots based on the mission: robot 1, robot 2, robot 3. And this is the RGB information from the camera attached to the robot's front. And this is the lander. Yeah, so this is about that. And last one is ROS and point cloud. So in order to visualize the point cloud, I had to use ROS. So whatever the data I'm getting from the RGBD camera there, I'm able to map always with respect to the lander. So if you have a fixed frame, no matter where the 3 rover goes, it always, whenever it maps, whatever the point cloud data I'm getting will always be the fixed frame. So we can use that for mapping the whole moon. So that was the idea on this. And yeah, next stage I'm planning to implement, next semester I'm planning to take a multi-agent reinforcement learning control course. So hopefully in that I'll be learning more about the algorithm side, and I'm planning to implement on mapping, coordinated mapping of the stray robots. Yeah, thank you.
Thank you very much. Yeah, that was great. I wanted to mention also that all these contributions are available here. You can see them on the Space ROS project demos repo, and then all these are pull requests with this particular label here. Next, we have David Dorf, and then on deck, please, Davide, if you can be ready. David, all yours.
Yeah. So my partner Katie Hughes and I made a repo called Space ROS GZ Demos. I can share my screen real quick. Can you see it?
Yes.
Cool. Okay, so I can just kind of step through the video. Don't have to show the whole thing. I think our design philosophy on this. Oh, it's not playing the video. It's not good. Oh, there we go. Okay. That's weird. Sorry. Maybe just refresh it. Yeah. So our design philosophy on this was kind of to give users a bunch of robots, models, and worlds, but not necessarily write programs for them. Because we thought in the spirit of demos that people should be free to write any control software that they want for these things. So really what Space ROS GZ demos is a collection of worlds, robots, and launch files for controlling those robots with bridges to topics from Gazebo to ROS. So in this world, this is Mars. Here you have the Perseverance rover and the Ingenuity drone, which you can kind of see over there. And you might notice that there's RGB and depth cameras for both. And you can control the joints on Perseverance, have it run around, Ingenuity can fly, has the, I forgot which plugin exactly it was. I think it was possibly like the helicopter or, I think it was the helicopter plugin. And this is the moon, so it's a bunch of rovers. This one was used in the subterranean DARPA project. And so these models, I was afraid that, a lot of the work here was going to be making the models. But in reality, there's a lot of models out there. Like these ones, for example, they're just out on Gazebo Fuel, very easy to use. And the Perseverance and Ingenuity ones were actually from NASA. They made URDFs, and then converting them to an SDF wasn't too bad. So it's very helpful. And then, there's a lot of assets out there for worlds as well. Some provided by NASA, some just by freelancers out there, open sourcing their work. So this was meant to sort of be like a construction robot scenario. If you wanted to make a moon base, you might want to have rovers that can clamp onto struts and stuff and then drop them off at a location. This is the ISS, and then a capsule that you can actually navigate with thrusters. I'm sure the thruster plugin was meant more for water purposes, but in this case, I just used it for like actual thrusters for a space capsule. So it also has a LiDAR. Most of these have like some sort of camera or LiDAR in the example, but that can be used to sort of use the thrusters to align to the thing. Martian, sorry, just got a question. So all of these demos have the gravity of the planets, but I didn't set any atmospheric parameters. I forgot if I set density for the atmosphere. If I didn't, make a pull request because that would be very cool. But I don't exactly remember what I set up the plugin with. But that would be really cool if I did not do that. And then Enceladus is just, I don't actually know. I don't think many people know what the surface, or anybody knows what Enceladus actually looks like on the surface. But this is my guess. It's a submarine that can, in the case of exploration on Enceladus, could navigate and map out what's going on down there. I think it's a pretty good candidate for having life out in the solar system. So I chose that as a potential example. I think Europa is, Clipper is a big mission, but I'm concerned about the radiation that exists on Europa. Didn't do Europa example, but so this is effectively sonar because it's underwater, but I just used the LiDAR plugin. As far as division of labor between me and Katie, I think, so my job is like heavily Gazebo focused, but we're both super proficient at ROS. So we both worked on the ROS launch file side together, as well as like messages and topics. And then Katie knows a lot about like GitHub CI/CD stuff and Docker, and I don't. So that's sort of how the division of labor spread out. Another question. Thanks, Trisha. feel free to check it out. This is, I think, our side of things, but I think there's also an official like Space ROS repo that has it now. So definitely check that out. Yeah, thank you.
Thanks a lot, David and Katie. Did you, based on Trisha comment, did you win the grand prize?
Yeah, we ended up winning. So
congratulations!
Awesome. Thanks for having this opportunity.
Of course.
We both worked at like NASA a while ago. At one point, basically just like during university. So this is really cool. I think we like space a lot, and this is an awesome opportunity.
Excellent job. Sorry, somebody raised their hand. Maybe that was a mistake, but we don't have a lot of time for questions. So if we have time within those 5 time slots, that's great. But if not, let's just move on. So next, thanks again, David and Katie. Next is Davide. And then on deck, Baris, please be ready. Are you ready, Davide?
Yeah, I'm ready. Can you hear me?
Yes.
Okay. Hello everyone. I'm Davide Zamblera, a recent graduate from Politecnico di Milano in space engineering. So my contribution was mainly focused on helicopter-based robotic system. And in particular, I wanted a contribution that had the features of modularity, so it could be upgraded with time, and it was can be broadly applicable. So in particular, I chose the Ingenuity Mars helicopter for its numerous record and its significance in planetary exploration. So basically, the model is composed of 3 main components that can be swapped with your own models when you develop them. And so I choose Gazebo for its ROS integration and ease of use. So the first part is the modeling of the downwash. So the continuous airflow that is needed for generating lift, and this is based on momentum theory. So it works until the stream tubes here in the image are well defined. So possible future contribution will be to extend it for when there is a vortex generation, especially during descent. And then we have the blade motion modeling. This part basically is the way the helicopters decides the direction where it will go. So with modifying the cyclic pitch controls, you can modify the distribution of aerodynamic forces, and so the inclination of the actuator disc. And in this case is implemented as a simple hinge spring model. And finally, we have the computation of the forces. So we have the sum of the inertial and aerodynamic contribution, and they're calculated with respect to the wind up frame. And then with a simple transport formula, they're applied on the link frame. And the density is actually obtained from a separate Gazebo plugin. So for the usage, you basically, it is not limited to the Ingenuity helicopter, but it is broadly applicable. And so you first define the position of the rotor with respect to the link frame. Then you choose the various submodels from those that are implemented, and you set the various parameters for the blade and the rotor. And finally, you can select the atmosphere model. In this case, it's a simple uniform density. And finally, you can try out the operation demo, but because of the nonlinear dynamics, it's actually pretty difficult to fly around. Otherwise, you can use the various topics. You have the actuator topics for the top and bottom rotor, and the various sensor topics. And so finally, to contribute, you can subclass the various base models to add more accurate dynamics. Or there are also the need to develop more accurate dynamics, like the coaxial rotor interference between the inflow of the top and the bottom rotor, and update the teleoperation UI and improve command detection. And so here are some links that you can follow on the pull request and my GitHub. Thanks for your attention.
Thank you very much, Davide. And sorry, I forgot to do a proper introduction. So you're Davide Zamblera from Politecnico.
Yes.
Yeah, thanks again. Yazici, sorry, Baris Yazici from Franka Robotics.
Baris Yazici, yes.
Next speaker. Yeah, whenever you're ready.
Can you see my screen?
Yes.
Yeah, so I will present my Ingenuity simulation and control. So my project for the NASA competition. And so coming back to the motivations and challenges for building this project, this was successfully done by NASA. It was the first part flight on another planet, and it was successful. So the challenges of building this vehicle is that it's only in the NASA there is only the 1% of the world atmosphere, and it's very thin, and the lift is basically much less than the world. Therefore, the weight of the vehicle needs to be really low, 1.8 kilogram, and it needs to drive autonomously. It cannot teleoperate because there is a huge delay. So my contribution to this is building a flight simulation, which is calculating the lift and drag forces based on the airflow and the angle of attack, and also the atmospheric pressure of Mars, plus the material properties. And I also built an automatic altitude control with PID. So the first thing is the collective control. I will present you. The collective control is changing the blade angle of attack uniformly over the full rotation. Here you can see I'm changing the desired altitude. This is going through the automatic altitude control, and now as you can see, the Ingenuity helicopter is landing. The altitude, desired altitude here is now 0. So the collective control is changing the altitude. And similar to the collective control, cyclic control also changes the blade angle of attack, but it changes it variably throughout the full rotation. So it creates an non-equal lift over the full rotation. At some position of the blade, there will be more lift, and some other position it will be less lift. So the whole body will tilt, and the whole vehicle will follow this tilt direction. Now it's going sideways. It can also go forward and backward. Actually, it will also now go back to left. So here you can see also the automatic collective control. So the desired angle, desired altitude is set to 10 meters. So the vehicle can keep the 10 meters altitude. So the cyclic control and the collective control, they are not mutually exclusive. They can be controlled at the same time. So now I change the longitudinal cyclic input, and now the vehicle is going to the other direction. Sorry, the lateral cyclic control. So coming back to the architecture, what the user can input to the plugins. So in the middle, you can see the Gazebo plugins. There are 2 plugins that I developed customly for this project. The first is the flight control plugin. This is an automatic flight controller deciding giving an angle of attack, so the collective input. And the second plugin I developed is the flight simulation plugin, which is calculating the lift drag forces around the hub of the motor, the vehicle. And this goes to the Gazebo physics engine. It applies on the Ingenuity model and goes back to the flight simulation plugin. And user can input the desired altitude through the flight control plugin. This will keep the desired altitude with the collective control, and the cyclic control enables the vehicle to go sideways, forward, and backward. How you can use these plugins? It's pretty easy. You just need to put it in your SDF model for your model. So it doesn't need to be an Ingenuity model. It can be also another helicopter model. It doesn't also need to be a coaxial helicopter. It can also be a normal helicopter. And left one is the flight altitude control. This is basically the automatic flight control, which I designed with PID control. It keeps the published desired altitude. Here it's 25 meters. You can change that. And the right one is the flight simulation. You can basically give the flight properties like airfoil characteristics, the environmental parameters such as Mars atmospheric density. Of course, the angle of attack can be changed throughout the simulation. So for the future work, I would really like to make it like get like a trajectory from the user and then apply this trajectory to the helicopter, move from one position, take off, and then land. So the second thing I would really like to do is like use the limited vision and add like noise to the sensory inputs and to develop like a more sophisticated control algorithm, which we can maybe in the future use it in Mars or some other planets. Visual SLAM. So you can see on the right, this is a photo from NASA. They analyzed the image to pick the key points through ICP algorithm, and through that they can understand which directions they are going, what's the velocity of the vehicle. So we can extend that. We can do mapping and we can do localization in simulation. This will be a good position to implement and develop on these algorithms in the simulation, and then develop and then deploy to the real world. So thanks a lot for listening.
Thanks a lot, Baris. Just really quick, were you aware of the lift drag plugin that exists in Gazebo?
Yes, I actually built on top of that.
Okay, awesome.
So yeah,
I was just out of curiosity while you were talking about it.
Yeah.
All right, thanks again. Next is Jasper Grant from Dalhousie University Intelligent System Lab. And then next talk is going to be Munir, if you can get ready. Oh, Jasper.
Hello, can everyone hear me?
Yes.
Okay. And can everyone see my screen? Should I do that right?
Yes.
Okay, perfect. So, my name is Jasper Grant, and sorry, I don't know. Are you looking at the actual slideshow or the presentation? I don't know why it's.
We do see your slides. Oh, sorry, not the entire presentation, just the
PowerPoint?
the full screen presentation, if that's what you mean.
Full screen presentation, you said?
No,
Or,
no, we're seeing.
Yeah.
We're looking at your slides.
sorry, 1 second. I think I clicked the wrong one there. Entire screen. There we go. How's that? Is that working?
Yeah.
Perfect.
That's better.
Perfect. So my name is Jasper Grant. I am an engineering training and master's student at the Dalhousie Intelligent Systems Lab. And my project is the Apollo 15 lunar roving vehicle simulation. And I chose to do the LRV because I've seen a lot of rovers. I've seen far less manned vehicles simulated on the moon, probably because this is the only real manned vehicle that was made for the moon. So I was very interested to see this simulated. So who am I? This is just a shameless photo to show off a photo of me with the LRV there because I got to see it in Washington last weekend. Dalhousie University on the east coast of Canada I am a master's student of electrical and computer engineering. This is my first open source contribution, which I'm super excited about. And yeah, I got to see that at the Smithsonian Air and Space. Definitely worth a check out. So the rover. So I did not make the mesh for this rover. I got it from the Deutsches Museum, which hosts it on Sketchfab. What I did do is I sliced it up into different individual pieces in Blender to make it into an actual moving model, which took me a while because I hadn't used Blender before for that, at least. And I was able to get all of the dimensions and masses, etc., from NASA. So that was like really cool to kind of see this thing go from a single mesh into, you know, an actual moving model. The other thing I added to this project was the terrain. The traditional Apollo 15 landing site model that's part of the Gazebo models repo, I was not that happy with it. You can see it there on the bottom left, because as soon as you zoom out, there's a lot of like repeated tiling. It doesn't have that much detail. The lights look a little bit weird for the moon, so I wanted to make some changes to it. So I took the texture up left and I replaced it with actually a different texture that's also hosted in another Gazebo repo, GZ rendering, that is just a lot nicer, I think. I also scaled it up in size. I added a normal, which kind of gives it a nicer kind of texture to it at a smaller scale. And you can see my improved landing site on the right there. I was quite happy with how it looked, and you will see in the later slides how it looks from the actual surface. So that's what it looks like there. I was quite happy with it. The demo itself includes an Ackerman controller to steer the lunar rover. The wheels have wheel odometry. There's an IMU implemented, and there are 2 cameras, and you can see one of the views from the back camera there on the right. For future work for this, I would really like to actually make the cameras like a little bit more controllable, because right now they're just static, but they could totally like actually move around. This is a simulation which kind of represents the start of my master's research here, and I am very excited to kind of take this simulation and see what I can do with it, see how far I can go in different respects for it. So thank you.
Thanks a lot, Jasper. That's a great project, and also good luck with your master.
Thank you.
Let's see. Next is Munir Azme from Element Robotics. And then next on deck, Jasmeet, if you can get ready. Munir, all yours.
Yep. Can you guys see my screen?
Yes.
Cool. Hi, everyone. My name is Munir. I'm a robotics engineer at Element Robotics. We are a space robotics startup based in Melbourne, Australia. And one of the projects we are working on is the Trailblazer mission, which is based around building Australia's first lunar rover. So LunarSim was our entry into the Space ROS simulation competition and is based in Gazebo. The main goal of the project is to provide a platform to test robotic systems in an environment that is representative of the moon. So there's quite a few lunar robotic missions that have been planned, particularly within the Artemis program. And so it's important to have a way to easily test these systems. In our demo, we've simulated a region near the south pole of the moon, since this is a particular area of interest for future missions. So yeah, we've implemented a few key features that would be important for robotic system development. Firstly, accurate topography, which would impact the maneuverability of a robot. Next, realistic terrain appearance, which is getting the texture of the surface to look realistic to a vision system and reflect light similarly to how lunar regolith would. And lastly, realistic solar illumination. Since there are very low sun elevation angles near the South Pole, this can cause high contrast between bright and dark regions, which can be tricky for vision systems. So yeah, accurate topography is important because robots need to be able to navigate and traverse uneven terrain that we see on the moon. So we use digital elevation models, or DEMS, which are 2D representations of the elevation of the surface. We sourced the highest resolution ones we could find, which have a resolution of around 5 meters per pixel. and they were captured from the Lunar Reconnaissance Orbiter. We then used the Gazebo height map feature to integrate it into the simulation. So providing a representative terrain texture is important since it defines how light reflects off the regolith. And in reality, regolith can have a high reflectivity, which can cause difficulties to vision systems. And we did this, we achieved this by first deriving the surface normals from the DEM and then blending them with a higher resolution sand texture, which gave us a rougher surface that you would expect on the moon. And yeah, here you can see the effect of the improved texture in Gazebo. So now that the surface reflects light in the right way, we still need the direction of sunlight to be accurate. And this is important, particularly at the lunar South Pole, since the low elevation angles cause long shadows and high contrast. And our systems need to be able to handle this. So the animation in the top right was created by NASA, and I think this visualizes it quite well. So in order to replicate this, we used the Horizons application, which was developed by JPL, and this provides the trajectory of the sun in the lunar sky throughout a lunar day, also known as ephemeris data. We then loaded in the sun as a Gazebo actor, which visits the positions defined by the ephemeris data. And you can see the differences in the lighting throughout the day in the simulation. So yeah, here's a short little video of our rover navigating around some rocks that we added into the world. And yeah, that's the end of my presentation. Here are a couple links to the demo PR and the documentation PR. And yeah, happy to answer any questions through my email as well. Thank you.
Thanks a lot, Munir. That was great. Maybe we have time at the end, so let's skip the questions for now, just to make sure that everybody has time. But yeah, thanks again. Let's move on with Jasmeet Singh from Peer Robotics, and then next on deck, either Roving or Stevedan, please. So Jasmeet, are you ready?
Yeah, hello everyone. Can you hear me?
Mm-hmm.
Yeah, so I'll just share my screen. Okay. Yeah, is my screen visible?
That looks good.
Okay. Yeah, so hello everyone. Our submission was related to making some custom models and custom plugins for Gazebo that helps us make a realistic simulation for the planet for extraterrestrial environments. So I'll just quickly start. So first, here's an example of one of our custom models that we made using data from the HiRISE telescope, which is aboard the Mars Reconnaissance Orbiter. We used the DEMs from the HiRISE data, imported it in Blender, and used a displacement modifier to create the models which you can see here. And similarly, we used the data from the LoLa imager, which is aboard the Lunar Reconnaissance Orbiter, to create a model of the lunar terrain. And all these models are available in GZ Fuel as well, so they can be downloaded and you can set up your own simulation using them. Apart from these models, we created some custom plugins. So this is one of the first plugins, which is called the Daylight Manager plugin. This plugin actually moves a sun-like object around the world according to the time and latitude settings that you have. And you can set a preset planet model. We provide like Earth and Martian models as a preset. You can scale the time using a GUI that is also provided. And you can see in this GIF that sun model is moving around the world. It causes changing in the lighting, and also it changes in the shadows all over the terrain. And this plugin also changes the color of the scene so that it can match the changing color of the sky. So this GIF currently shows the presets that we have for the Martian sky colors according to the time of day settings, and also so like the GUI can be used for tweaking all the settings related to. We can also like speed up the time, or we can change the place according to which according to the planetary terrain. And also the time is published as a clock on a GZ topic, so it can be used by other plugins to, so say like for example just like a plugin which can be used to determine the humidity or the environmental factors depending on the time of the day. So to simulate that setup, we can use the clock that is being published by this plugin. And also we added lens flare system plugin to the rover's camera, and it gives like a beautiful visual of the camera sensor, and also like creates a more realistic setup, because as the time of day changes, the rover's camera may encounter the sun directly, and it will like cause lens flare artifacts into the camera. So this lens flare system was contributed to GZ Harmonic, like I contributed it a while back, and we added it to the camera model for the rover. Apart from that, we also added a dust manager plugin, which uses particle emitters to create dust. And the dust manager plugin finds a dust generator model, or it can be added using the resource spawner, and it starts emitting dust. We can just like toggle the dust or the wind settings for the emitter, and we can. This plugin also comes with a GUI, which can be used to change the density or the velocity of the dust particles, and it can also be used to change the color of the dust particles, so we can match it according to the color or the texture of the terrain that we are using. And yeah, so the particles also affect the sensors on board the rover. So for example, you can see the RGB and the depth camera images on the right, and we can see like the dust is affecting like creates a noisy image for the depth sensor as well as for the color sensor. So yeah, this is from our side. So thank you.
Thanks a lot, Jasmeet. Yeah, that looks beautiful. Yeah, that was a great contribution. Thanks a lot. Now we have Roving, Baran, and also Stevedan, Ogochukwu, Omodolor.
Steven.
You probably say much better than me, but whenever you're ready.
Oh.
Okay, so yeah, I'll be presenting my colleague our entry to the challenge. Can you hear me well?
Yes.
Okay, great. So we provided a lunar South Pole exploration rover simulation based on the real NASA Viper mission. Steven, can you go to the next slide? Thanks. So we choose this mission because there's great interest at the moment for the lunar South Pole, because of the potential presence of water ice in the permanently shallowed craters. So our simulation includes a fully controllable rover model, a Gazebo world, and a set of plugins to simulate the power generation and usage. So the Gazebo world is a 1 square kilometer terrain based on the location where the real rover was planned to land. The sun is low on the horizon like the real environment, and of course we get lunar gravity and no atmosphere. So it was generated using NASA elevation maps of the South Pole from the Lunar Reconnaissance Orbiter, especially the Mount Muten area. It was also previously called the Litnitz-Bed. The rover model itself is based on the real Viper rover. It includes 3 simulated solar panels using a plugin that my colleague would explain just after. The model also includes the full navigation sensor suits from the rover. So we get, of course, IMU and odometry, but also a lot of cameras. We base ourselves on this paper to get them right. So we have a pair of front camera that can pan and rotate around the masts. We have a pair of camera at the back, called the aft cam. And in each wheel well, there's a camera for detecting the potential hazards around. They are called the haz cams. So the model includes also a lot of controllers, and we provided the control node with a velocity input. So what they actually, so the rover has 4 independently steerable powered wheels that allow almost holonomic range of motion. So we can rotate on place with only angular velocity command. We also have like a crab-like motion with only linear velocity command. And then we can combine the two to get some kind of Ackermann drive motion.
Okay. In addition to the Gazebo model, we also included some plugins to handle power management and power generation for the robot. These plugins include, as my partner mentioned earlier, solar panels, RTG for the power generation, as well as rechargeable linear battery, and also sensor power system plugin for the power storage and power management. Okay, for the power solar panel plugin, the idea of the plugin is that it allows you to simulate power output based on the panel's orientation with respect to the sun. And on the video on the right, you can see, for example, each of the plot represents the power output of each panel, and we can observe that the power output changes depending on how much of the panel is in direct contact with direct sunlight. For example, when one of the panel loses contact with the sun, its output drops to 0, while the others continue generating power. And also, we also included a simple RTG plugins, and the idea is, unlike the solar panel, you can generate a constant power supply to the robot. Okay, in addition to the previous plugins, we included the rechargeable battery plugin, which is based on the linear battery plugin from Gazebo. The key difference is that it allows us to set like multiple power sources in order to charge the battery. You know, in this case, we use the RTG and the solar panel as power sources. And also the power begins to drain as soon as the robot starts moving, or you can set this value from a topic. You can define this in the XML file and the configuration file. Finally, we included the power system plugin. The way it works is it works in conjunction with the rechargeable battery plugin. The idea, it allows you to manage the sensor power consumption. It lets you assign, for example, specific power loads to each of the sensors and be able to deactivate them to save energy. This is quite also useful in real missions. And also, there's also the possibility that if the power battery runs low, you can automatically shut down all the plugins to conserve power. And this is quite also useful because you can see the example of the Voyage 1, where thanks to the fact that you were able to shut down some of the cameras, you were able to like extend the robot lifespan of the satellite. That's all. Thank you, everyone.
Thank you.
Thanks a lot, Robin and Stevedan. Yep, that looked really good. Thanks again. And last but not least, we have André Horsula from University of Luxembourg.
Hello, can you see my screen?
Yes.
Great. So yes, thank you. My name is Andre. I'm a PhD student at the University of Luxembourg, and I will present a bit about generating procedural assets in Blender and how you can use them inside your Gazebo simulation. So why am I talking about procedural generation? Well, the availability of data sets for space is improving, but it is still limited in scope and resolution, especially for certain applications such as manipulation. At the same time, procedural generation offers a way towards domain randomization, where we can simulate diverse scenes with infinite variation, which is especially suitable for workflows such as reinforcement learning. But how can we generate such procedural assets for space? Well, there are several tools. I think Houdini is one of the more popular, but the open source Blender also has this functionality through its geometry and shader nodes. This can be used to create procedural pipelines, which are meant to be artist-friendly, but at the same time, I think they can get a bit chaotic as the complexity increases. In the video below, you can see the generation of terrains with this approach. But how do we bring these assets into Gazebo? Well, we can generate a mesh, we can unwrap the UVs, we can bake the textures, perhaps render a thumbnail, and then export everything as SDF. It might sound like a lot of steps, but the demo contains a Python script that fully automates these in a headless manner for any number of variations. And on the right side, you can see these generated assets being inserted directly into Gazebo with the resource spawner plugin. And here are two very minimal demos using these assets, one for Moon, one for Mars, running inside Gazebo Ionic. And I hope this gives some idea of how the environments could look like inside your Gazebo worlds. The repository is below, and you can use it to run these demos yourself if you'd like to inside Docker. Or you can scroll through it and see how you can generate and customize the model yourselves. I'll just forward it just to show you the creator. And yeah, so this model is actually from Fuel. Both of them are from Fuel. Okay, and I'll just end on this slide showing you that the same approach can be used more for than just natural scenes. It can also be used for artificial objects such as these CubeSats, which are generated through the same process. Thank you.
Thanks, Andre. And I'd like to give a huge thanks to everybody who contributed to this talk. That was quite a sprint in the same spirit of the NASA sprint, but totally worth it. Love to see all these projects put together with Gazebo as the common denominator. Yeah, big congratulations to everybody. Just one last comment. If you see this talk, maybe the video of this talk, and I missed you, like I think I went through all the Gazebo contributions to this challenge, but you know, I might miss you. If I miss you, please reach out to me, and then we can do we can squeeze your talk in the next Gazebo meeting. We don't have time for questions, but we made it. So thanks everybody, and see you next time. Ciao.
Bye.
Thank you. Bye.
Thanks. Bye.
Thank you.
Thank you.
Thanks,
See you.
everybody.
Bye bye.